All right, welcome back. In this lesson, we're going to be going over this topic called volumes of solids of revolution. And we're going to actually focus first on the disk method before in later videos going over this thing called the washer method. So let's see what it's all about. I'm going to start out with a problem and just kind of lead you through the process, then go over the general idea of what this is all about, and then finish off with applying that general concept to one more problem. So it's going to be a long journey together, but it'll go quick because we're going to have some fun. So let's do it. We've got f of x equals 2 is the region, part of the region, x equals 0, x equals 6, and y equals 0. The instructions say find the volume of the solid made by revolving the following bounded region about the x-axis. So what's different between this and what you've done before with finding area is you're actually going to have like an area of a region, and then you're going to revolve it about something, causing you to have a three-dimensional object, which is really, really cool. So what we've got here is f of x equals 2, and that's just a horizontal line, right? And so we're just doing a rough sketch, right? Something like that, just sketch out y equals 2, that's right here. And the reason why I'm not going into the second quadrant here is because we're bounded at x equals 0, right? So we're bounded at x equals 0 like that. At y equals 0 below, so basically it looks like getting a rectangle here, right? And then x equals 6. Oh, so let me neaten this up here. And you end up with a rectangle, but we're not finding the area of the rectangle. We are revolving it about the x-axis. That's why these are called volumes of solids of revolution. They are solids formed by revolving them, and we're finding their volumes. So when we revolve a rectangle, right? Imagine taking a rectangle. I'll take just my graphing calculator right here, right along my arm, right? If we revolve that like this, and you go around like that, you end up with a three-dimensional object, one that is a cylinder. So you don't need to be able to draw these things out perfectly when you revolve them, but it's nice to be able to just draw a rough sketch every once in a while. So what I do is just draw a little dotted line here, almost like a mirrored reflection of this. And then I show revolution. So we end up with this can-looking thing, right? In other words, a cylinder. Very cool. So I end up with a cylinder. Now, you might be like, well, I know how to find the volume of a cylinder. It's pi r squared h. That's all well and good, but what I want you to be able to do is find volumes of objects that aren't necessarily nice geometric solids like this. So, like we did in area, we're going to put in what I call my rep-rect, or representative rectangle. That's going to be the distance from the outermost part of this region into the axis of revolution, right? What you're revolving around or rotating around. So we're going to draw in that rectangle from here to here. And when you revolve that rectangle, right, this thing, you're going to end up with a disk, right? When you revolve a rectangle, as we just saw, we end up with a disk. Those are called cross sections. They're little sections or cuts of a can. Imagine taking a can and taking cuts of them, right? So what I like to do, at least for the first few examples, is draw in that disk cross section. You'll get these tiny little disks, almost like little coins, like that. And let's just figure out what the volume of this disk is normally. Okay, well, here it's very important to note that the width of that rectangle is dx. So this disk has a little height right there, a thickness of dx, really, really small width. And then this right here is the radius. Okay, so I call that big R for the radius. That's the distance from the outer edge here of the region to the axis of rotation. Now, if we think about this, the volume of any disk is pi r squared times the height. Why is that? Well, if you think about it, I've got a glass of water right here. Here we go. If you take something that is cylindrical and you take the area of that water, it's a circle, that's pi r squared, and then you raise it h high. Imagine pouring water into that. You're gaining a volume, right? And so that gives you volume. So in terms of this particular figure, that's pi r squared, and the height is the distance that basically is measured between the two bases, or the two circles in a cylinder. And so that'd be pi r squared dx. Now, imagine taking that one disk right there, and you're adding up infinitely many of them from left to right, stacking them up, like putting coins inside of a coin sleeve, just kind of filling up that space. So how do we add up infinitely many tiny things? You'd integrate. So we're going to integrate pi r squared dx. Now in this particular problem, we need to integrate from the leftmost bound to the rightmost bound of the region, which would be from 0 to 6. Oh, like imagine sliding up those coins from left to right. Pretty sweet. So most teachers will teach this by taking pi outside. We'll integrate it from the left bound to the right bound. R in this case is the distance from here to here, the distance from the outer edge to the center. That's a radius. right? It's the distance from the outer edge of a circle to the center. And so that's going to be this minus that, which is 2 minus 0. So that'll be 2 minus 0 squared. I'm going to write it as 2 minus 0 dx. And now here's the cool part. We're done, right? That's the setup. That's the new part. The rest of this is just integrating like normal. So we've got pi times the integral from 0 to 6 of 2 squared, not bad, is 4, and then we have dx. We're going to integrate that. So that's going to be pi times 4x, evaluated from 0 to 6. And then when we plug all that in, we're going to get, well, 4 pi times 6 minus 4 pi times 0. Okay, so that ends up giving you 24 pi. And we don't have any units. It's just the volume, 24 pi units cubed, if you will. And that's it. That's some concept for you, too. So in this next slide, I've kind of already gone over the concept. I'm going to generalize this for you. The general concept of the disk method is this. When you have a region, and I've given you this random region here, that is rotated about, and we'll just do the x-axis in this particular case, you always want to identify what the radius is. And that radius is going to be the distance, again, from the outer edge of the region all the way down to the axis about which you're rotating, right? And that's going to be r. And so that I like to imagine is a really, really thin rectangle. When you rotate that, you end up with a disk, right? I'm going to draw that disk nice and large right here. And that disk is going to have a radius, right? That goes from, again, the outer edge to here. That radius is the same exact math you were doing when you were finding the heights of the rectangles, when you're finding area. Now, how do we know that it's a disk? Well, when you revolve this thing about the x-axis, you end up with no space between, well, this region and the axis you're rotating it about. So there's no gap. Basically, any area, this whole region here that you're rotating about the x-axis, it becomes volume. And it's flush with the thing you're rotating about. So there's no space at all, and it all becomes solid mass, if you will. So look at it geometrically always, right? Always keep geometry at the forefront of your mind when you do this stuff. Here's your radius r. In this case, that's going to be f of x minus 0, right? In this case, it won't always be f of x minus 0. We'll see in other problems it could be f of x minus something or something minus f of x. We'll see all kinds of stuff. It'll be fun. All right, now here, this in this case is dx. That's the thickness. That'll always be the thickness, either dx or dy if they're disks flattened like this, being stacked bottom to top and not left to right. But it's always going to be d something, a very small thinness. So then we know that the area of this part of the disk right here, that area, is equal to pi r squared. And then you multiply it by the thickness, and that gives you the volume of one of those disks. As I mentioned in the last part of this video, we want to then add infinitely many super tiny disks. That's what integration does. We're going to integrate it all. I factor out the coefficient, you get pi r squared dx, and I add up or stack those disks, infinitely many tiny disks, from A to B. And that is your general formula. A couple things to remember. The radius is always measured perpendicular to the axis of rotation. What that means is, if we're rotating about the x-axis, we draw a rectangle this way, and if we're going about the y-axis, we draw it this way. More on that in later videos with the y-axis. The region is flush against the axis of revolution. That's what I mentioned before. If your region is flush against the thing that you're revolving, there will be no holes when you revolve it. There will be holes later when we look at the washer method. And then, as I said here, always let geometry lead. What I mean by that is, don't just memorize the process I'm showing you. Understand that what you're doing here is you're taking basically a really thin disk, a cylinder. You're finding the volume of it, and you're adding up infinitely many of them, right? And the infinitely many part's the calculus. The volume part, that's geometry. All right, so before we end this, I want to apply this concept one more time, and then we're going to go into another video, and of course I'm psyched to go there. This says find the volume of the solid made by revolving the following bounded region about the x-axis. So we're going to go about the x-axis like so. I'm going to draw the region like we do in area. So 2x, I'm going to just kind of draw a rough sketch like that. X equals 0, that means we're restricted here at the y-axis. That's why I did not continue to draw this line into the third quadrant. X equals 4, so let's just say that that goes right here. Makes a triangle and the x-axis. Oh, so here's our area. We're going to be revolving that thing. Now, you don't have to know how to revolve this thing. As I said, you could just draw on your radius right here. But for the first few examples, I want to at least show you roughly what this thing will look like. So when we revolve it, we end up with basically like a solid cone, right, is what you end up with. This very solid cone, I mean, you'll get a little bit of volume here. It just kind of goes around. And so we'll end up with the volume of a cone, just a basic cone. But we're going to do it with calculus. So here's your radius, and I'll do that in a different color. So your radius, again, is the distance from the outer edge of the region to the axis at which you're revolving about, being perpendicular there. When we revolve that thing, you're going to end up with that beautiful disk in here, right? You're going to get a disk all in there. So I like to draw out that disk when I'm first learning this stuff and when I'm first teaching it, like so. And then here's the axis of rotation. And that distance right there is going to be r. Now what's r? Well, it's this distance from here to here. And it's changing. That distance is changing here. That's why we need the calculus. So the radius is this curve to the axis right there. Well, that's 2x minus 0. So I like to identify what my radius is first. It makes life easier. And now I'm just going to plug it into the template of pi times r squared dx evaluated from a to b. Okay, here we go. Pi times the antiderivative, or the integral. A is 0, right? X equals 0. And then we're going to get these disks that are being stacked, and they're growing as we go to the right. And they're going to go all the way till we get to x equals 4, where we'll stop with our disk growing. And then r is 2x minus 0, or 2x squared. Multiply by the thickness, and that will give us our volume. So let's go ahead and solve it out. It's not so bad. I've got pi times 4x squared. Ooh, all right, so that's not so bad. We can handle it. 4x squared dx. Let's anti-differentiate this thing. So when we integrate this, we'll get 4 pi x cubed, and that'll be over 3, evaluated from 0 to 4. Not so bad, right? Basic integration to this point. The new stuff is done. I'm going to plug in 4 into this thing, and I'll get 4 pi over 3, all times 4 cubed, minus 4 pi over 3 times 0 cubed. First fundamental theorem calculus in all its glory. The 0 cancels, you're left with 4 cubed, which is 64, times 4, which is 256, and then you've got pi over 3. Get used to seeing some funky answers. When you get nice answers, that's when you should worry. All right, that's it for this video. A little bit of a longer one, but chock full of goodness. I will see you in video 2. We'll go over a couple more examples, and then eventually we'll be revolving disks around vertical axes. Very exciting. See you there. Peace.